Okay, so in the last video, we talked about the concept of work. And remember, work is when a force can transfer energy to or from an object. And then we also talked about the equation for work. And the equation for work looks something like this. We have W, that's work, is equal to force times distance. Okay, so when you apply a force over a distance on an object, you can do work, meaning you can transfer energy to or from an object, and positive work corresponds to adding energy to an object, and then negative work corresponds to removing or taking away energy from an object. Okay, so in this video, we're going to talk about the work-energy theorem, which basically is going to connect the concept of work back to kinetic energy. Okay, and so I put the work-energy theorem here in bold, but I'm going to write as an equation here in just a second. So here's what the work-energy theorem says. The work-energy theorem says that the net work on an object is equal to its change in kinetic energy. Okay, the net work on an object is equal to its change in kinetic energy. Okay, so let's take a look at what that would look like as an equation. Now, for the purposes of this class, we're not going to worry too much about what is meant by network. But basically, network is what you get when you find the work done by all the forces on an object. And the problems we're going to be doing, the work given in the problem is equal to the network, and so you don't really need to worry about that too much. But basically, what the work energy theorem says is that the network on an object is equal to the change in. Now, the way we do change in is with the delta sign, right? Change in kinetic energy, and we know kinetic energy is EK, and so I'm going to write that EK. Now, this equation, the way it's written, doesn't really help us because, okay, that means changing kinetic energy, but we need to be able to solve problems with this. Okay, so I'm going to write this equation in a slightly different way that's maybe a little bit more helpful. So remember, change in anything is always final minus initial. Okay, when you talk about a change in something, it's always final minus initial. So delta EK is equal to the final kinetic energy, EK final, minus the initial kinetic energy of an object, EK initial. Okay, so when you're doing problems with the work energy theorem, basically what's happening is work is being done, either energy is being added to an object or energy is being taken away, and because of that, the kinetic energy of the object is going to change. Okay, either it's going to increase or it's going to decrease, and so you have two different values for EK. Now, just to remind you, kinetic energy, the equation for kinetic energy is 1/2 mv squared. Okay, and so here is the work energy theorem right here. And remember, when you see EK final, really that's 1/2 mv final. And when you see EK initial, you can think 1/2 mv initial. Okay, because the equation for kinetic energy is 1/2 mv squared. So that is basically what the work energy theorem says. Okay, so pause there and make sure you add that to your notes. And we're only going to do a few examples. These problems are usually pretty straightforward, but they can require some algebra. Okay, so we're going to do 3 examples, and hopefully you get a better sense for how to solve problems using the work energy theorem, and then you're going to have a practice assignment. Okay, so you should have that in your notes. Okay, so let's take a look at example 4. So example 4 says, as a 20-kilogram shopping cart, as I'm going through, I'm just going to identify my givens. As a 20-kilogram shopping cart with 500 joules of kinetic energy. So right off the bat, I know that's EK. Now I need to keep reading the problem to see is that EK initial or EK final. Rolls down the aisle, the force of friction acting on the cart does negative 200 joules of work. Now this is a problem with the work energy theorem problem. It's asking us what is the new kinetic energy of the cart. Now this is an example of where if you understand the concept of work, this is a very easy problem. Okay, so I'm going to solve it using the work energy theorem, and then I'm going to show you how you could just solve it conceptually. Okay, so this has to be the initial kinetic energy because that's the kinetic energy at the beginning of the problem. So we write down the equation for the work energy theorem. That's equal to EK final minus EK initial. We know that the work done by friction is negative 200 joules. It's negative because friction is going to take energy away from the car. It's going to make it slow down. We're looking for the new kinetic energy, which would be EK final. And the initial kinetic energy is 500 joules. So if I want EK final by itself, I need to add 500 to both sides. And I get EK final is negative 200 plus 500 is 300 joules. And that is the answer to the question. Okay, so this is a problem that you would solve using the work energy theorem, but you could solve it much faster if you just understood the concept of work. Okay, so remember, when we talk about work being done on an object, we're talking about either energy being gained or lost by the object. So when it says friction does negative 200 joules of work, that's basically the same thing as saying friction is going to take out 200 joules of work. So think about the 200 joules of energy. So think about it like this. If I have 500 joules and I take away 200 joules, then that leaves me with 300 joules, which is the correct answer. Okay, so either way you solve this is fine, but technically this is a problem you would solve with the work energy theorem. Okay, so pause there and make sure you add that to your notes. Okay, and we're just going to do two more examples, but they're going to get a little bit more difficult now, so make sure you're copying down everything that we do. Okay, so let's take a look at example 5. So we have a Mousetrap car here, which you might have built when you were younger. And it says an 8-kilogram Mousetrap car. Off the bat, I'm going to underline that. That's going to be the mass of the Mousetrap car. Uses energy from a spring to move. Now, when I see a spring, I'm thinking it has elastic potential energy in it. I don't know if that's important, but it does have elastic potential energy because there's a spring. Now it says, assuming that the car originally, that usually means like initially, so this is probably the initial speed of the car. It initially moves at 0.5 meters per second. That's going to be my VI. It says calculate the kinetic energy and speed of the car if the spring does 10 joules of work. Okay, so they're talking about work. When you're doing a work problem, either you're using the work equation, which we're not going to be doing here because it doesn't say anything about force or distance, or you're most likely using the work energy theorem. Okay, so that's what I'm going to start with. So I write down the work energy theorem. That's equal to EK final minus EK initial, the change in kinetic energy. I know that the spring does 10 joules of work. Okay, so this is going to be 10 joules. And the first question asked me to calculate the kinetic energy of the car after the spring does work. So I'm looking for EK final. So EKF is my unknown. What about EKI? Okay, so they don't give me the initial kinetic energy, but they do give me enough where I can solve for it. So remember, EK is 1/2 mv squared. So EKI would be 1/2 times the mass times the initial speed squared. And so I'm going to plug in there 1/2 times 8 times 0.5 squared. And that's going to be, let's see, that's going to be 0.25. That's going to be 2. Sorry, that's going to be 1. Okay, and so that means the initial kinetic energy was 1 joule. Okay, so I put a 1 there for EKI. So if I add 1 to both sides, that means EK final is going to be 11 joules. Okay, so I've answered the first question. Now the second question says, it says calculate the kinetic energy and the speed of the car if the spring does 10 joules of work. So I found EK final, but when it's asking me for the speed, now it's asking me for V final because they already give me V initial. Now they're looking for V final. So how do I find V final? Well, I'm going to use the kinetic energy equation to do that because EK final would be equal to 1/2 times V final, and I just found EK final. Okay, that was 11 joules. Okay, so now I'm just going to plug in, and now I have to rearrange to get VF by itself. Okay, so I do, let's see, half of 8 is 4. I want V final by itself, and it's being squared and multiplied by 4. So I'm going to divide both sides by 4, like that. So I'm going to go to my calculator, and I'm going to do 11 divided by 4. 11 divided by 4 is 2.75, and so that gives me 2.75 equals V final squared, and then I need to do the square root on both sides. Okay, so VF is going to be equal to the square root of 2.75, and that my calculator tells me that is 1.66 meters per second. And so that is the answer to the second question. Okay, and so that's like a full-length work energy theorem problem right there. Okay, so we use the work energy theorem, plus we also had to use the equation for kinetic energy to solve for everything that we're looking for. Okay, so you'll see problems like this on your practice assignment. Pause it there if you need to look at example 5 some more. Okay, so finally we're going to do example 6. Okay, so the question says, a girl runs up to a soccer ball which is sitting at rest. I see that context clue right away, sitting at rest on the ground, and kicks it. In kicking the soccer ball, the girl does 300 joules of work on the ball. They also give us the mass of the soccer ball is 0.4 kilograms. Okay, so this is the mass. Now the first question says, calculate the kinetic energy of the soccer ball after she kicks it. Okay, so I want you to try to answer the first part of example 6 on your own. Calculate the kinetic energy of the soccer ball after she kicks it. Okay, so because the soccer ball was initially sitting at rest, if it's not moving, it doesn't have kinetic energy, right? Because kinetic energy is energy of motion. So the fact that it's sitting at rest at the beginning of the problem is a context clue telling us that EKI is 0, 0 joules. Okay, so I can use the work energy theorem to do this, but I don't even really need an equation to do this because I can just think, okay, so let's think about this logically. I start with no joules of energy. The girl does 300 joules of work when she kicks the ball, meaning the girl adds 300 joules of energy to the ball. So if the ball starts with 0 joules and then you add 300 joules to that, that means the new kinetic energy is going to be 300 joules. That's the answer to the question. Okay, so hopefully that's what you got. Now, the second question says calculate the speed of the soccer ball after she kicks it. So now that we have EK final, I want you to pause it here and try to find the speed of the soccer ball after she kicks it. Okay, so remember kinetic energy is 1/2 mv squared. So I'm looking for the speed, so that's v. After she kicks it is going to be v final because v initial was 0. And so I have 300 joules. Okay, so EK is 300. That's equal to 1/2 times 0.4 times VF squared. And I want to get VF by itself, so I need to simplify. 1/2 times 0.4 is 0.2 VF squared. There's two things being done to VF. It's being multiplied and it's being squared. So I want to divide both sides by 0.2. Boop. Okay, and so I get VF squared is equal to 1500. And then to get rid of the square, I need to do square root on both sides. Okay, so the square root of 1500 is approximately equal to 38.7 meters per second. Which now that I think about it, is maybe not very realistic for soccer ball since that's like, 80 miles per hour or something. Maybe a little too fast for soccer ball, but hey, maybe maybe the girl works out. I don't know. Maybe she's Supergirl or something. Okay, so we have done 3 examples with the work energy theorem. Okay, make sure you have all 3 examples in your notes. That would be really helpful as you're doing the practice assignment over the work energy theorem in Canvas. Okay, so as always, please let me know if you have any questions, and I'll see you guys in the next video.